Testing. All right, cool. This is just a little intimidating for me since I'm not used to talking, least of all with the PA, and worst of all with an actual crowd in front of me. I will warn you, this presentation is probably going to be a little on the boring side because it was mostly designed with the intent and knowledge that a lot of people probably weren't going to be able to make this presentation at all. So, Wi-Fi networking done the right way or reliable links made easy? I really suck at titles. Yeah. Okay, that kind of got cut off. Anyway, who am I? Cell phone set to stun, please. I please myself. Let's just kill that. All right. Worked in a small wireless ISP, of course, vendor trained, which means we do it exactly this way, or God help us, you know, the FCC will get after you. Installed a small city WAN, which is a really nice way of saying that I was stupid enough to climb a ladder at my employer's insistence. Been in ham radio for 12 years, which doesn't really say a whole lot, but I've done a lot of research in this matter and a lot of antenna research and seen some really interesting things. And of course, infrastructure geek, which is actually one of the things that's cut off at the bottom. I'm willing to bet that's not quite set up correctly. Okay, here's the assumptions. Let me see if I can fix this somewhat better. I guess I'll just have to deal with the being cut off there. The assumptions, of course, are that you want to set up reliable links. You want this stuff to work where you can push traffic over it, you know, as reliably as possible, backbone links, that sort of stuff. The other assumption is you have a basic idea, more or less, of how radio works. You know, you put an antenna up here, you put an antenna up there. Magically, things just sort of happen. Wi-Fi is, in fact, radio, if you were not aware of that. And of course, down here at the bottom, which is cut off, you know that Wi-Fi is a form of radio and how to hook them up to antennas. So, oh, does anybody know what? Let's see. Is it in there? Okay, that's actually part that's cut off. It says, "Do you know that Wi-Fi is a form of radio, not PFM?" Does anybody know what PFM means? Pure freaking magic. Okay, you know what antennas are, how to mount them, and point them at something. Very, very important. Because if you just have it, you know, pointed off in some weird angle, expecting to talk across the street, that's just not going to cut it sometimes. Does anybody here know what a decibel is? Okay, that's one answer, but a tenth of a bell is correct. I've got another slide here, which is yeah. Yeah. I've got another slide here which has the which explains some of the what all that stuff is. Well, this is just wonderful. Okay, gain versus power. We have two types: antenna gain, amplifier gain. Antenna gain, you improve the signal directivity often greatly, which is at 2.4 gigahertz. It's fairly easy to get a high amount of gain in a physically small dish. On the lower frequencies, things don't translate quite as well, and in order to achieve the same results, you have to have really expensive hardware on the order of steel supporting structures and whatnot. Yeah, we generally speaking, the sky is the limit, but it's costly and useless beyond a certain point because you can only throw so much metal at the problem, and you hit the point of diminishing returns, as it's called, where you can still add metal, but you just don't get anything more for it. Of course, it's always advised to invest in metal, not watts, because usually it's cheaper to get an antenna. They tend to last long. They don't usually die or corrode, depending on whether or not you're in Florida. Amplifier gain, of course, actually generate more signal, but this gets a little interesting with the FCC because of some of the limits and rules in Part 15. Of course, it cut off the bottom half of the slide. I love this thing. Amplifiers are a lot more expensive than antennas, mostly for Wi-Fi. Usually the time you start talking about using amplifiers, you're talking about running either a nice big piece of expensive coax up the side of a tower, or you're talking about using a cheap piece of coax and using a $300 amplifier. And you just have to kind of gear that one for what you can get away with and what needs to be accomplished. And also, this gets a little tricky because depending on exactly what you're doing and what kind of antenna you're using, you may have to actually cut the power that you're transmitting in order to meet the FCC requirements for Part 15. Yeah. Again, put your signal where you want it, and sometimes make sure it's not there. Let's see. Down here, we've got best investment for networking at 900, 2.4, 5.8 gigahertz and beyond, typically expressed in dBi or dBd. dBd is usually a term thrown around by people who have familiarity with the dipole, which is a very simple antenna, and realistically, it's a standard from which all others are measured. dBi is the I stands for an isotropic radiator, which is basically a point source, which we don't have the ability to generate. And the closest example I can give of an isotropic radiator is the sun, because it radiates equally in all directions out from the middle. Okay, yeah, amplifiers typically cost about $300. If you're lucky enough to have a ham radio license, you can actually waste a lot more money than that, because you can buy amplifiers up to 100 watts, because it's red spectrum. That's the limit for hams anyway. But there's other issues to deal with. This is probably a little dated, since I think I've actually seen some 802.11g amplifiers. But one of the problems is that you have so much information in such a space that it can be a bit trying on the amplifiers just to do their job at using G, just because of the bit to hertz ratio. The 802.11b stuff generally just does its job and works. Okay, and of course, about half the slide. Extremely limited applications. Usually use amplifiers for backhaul stuff. We want it to work. We want it to be reliable at the expense of having a single point of failure up close to the antenna. Usually amplifier gain is expressed in decibels, as usual, and dBm, which is more of a value of the actual output power. Okay. This is really important. EIRP and ERP, effective radiated power. If the SEC decides that they want to talk to you about this stuff, it's probably a good idea to go ahead and find a lawyer in Washington just in case. The SEC is kind of one of those weird organizations when it comes to official correspondence. You can try to wing it on your own and may be able to get away with it, but if things start going downhill, it will be expensive. The bottom line here, which is cut off, is that they start at $10,000 for a simple fine. Unfortunately, that figure is many, many years old. They've been handing out $10,000 fines since, I think, the 60s, which, of course, meant a lot more then. But like I say, they don't like to mess around too much. Here lately, they've been pretty laissez-faire, but they used to really have some teeth. Okay, effective isotropic radiated power, EIRP, which, like I said, goes back to the whole thing about a point source versus the other. And ERP, effective radiated power, somewhat interchangeable. Not exactly, kind of, sort of. It's a legal definition, but mostly people use them interchangeably. EIRP is what the FCC rates everything in, because they believe that this is how much RF leakage you should be presenting, how much energy you're putting out there, and just polluting space in general. It's okay. The question is how EIRP is defined with with the directional antenna, and usually the way that's handled is it's simply the power that you're transmitting plus the antenna's gain. So, like I say, it doesn't change too much. It's still an effective multiplier. If you have a TV station transmitting at 60,000 watts and they have an antenna gain of like I think 14 or 17 dBi, you wind up with an effective radiated power in about a megawatt or so, which is why you can pick up the TV stations so well. And really and honestly, they do radiate a lot of power sometimes. Antenna gain. This is a pretty big important part, because as your gain goes up, the signal that you're actually transmitting becomes more and more directional. This is pretty well a constant thing. The higher the gain, the closer to a point, to a flashlight beam or a laser, the laser pointer things get. The signal becomes generally very confined. And when you, well, okay, the signal tends to resemble a donut or a torus in the case of vertical antennas, or a 3D ellipse in the case of a directional antenna. The higher the gain, the flatter the pancake. If you put a pencil on the table, or you put pancake on the table, you put a pencil in it, that kind of looks like some of these high gain verticals, vertical antennas, omnis as we call them. These are of course exaggerated figures. The green line over here is supposed to be a reasonably low gain antenna. Since this is a non-specific antenna, you can probably push these figures pretty far for exactly what you're looking at. But this is just an example of what the radiated signal might look like, or at least the coverage pattern. Blue, this would be your medium gain, and then of course the really high gain antenna, which just flattens it way out there. Okay. Larger problem with antenna gain is people tend to confuse gain with power and make very bad decisions. When I first got into wireless networking and doing this stuff for a living, one of the problems we had was that everybody and their brother would go out and buy a 15 dBi Omni, put a half-watt amplifier behind it, and just generally create a whole lot of noise in the 2.4 gig band. The 15 dBi antenna is not recommended, because what happens is you only have so much range that you can communicate on 2.4 gigahertz with reliably. And the problem is that that pancake winds up shooting out past your users right into the horizon in a space where you can't get a signal back from. So you wind up sending your power out there, but you can't use anything coming back. It just pollutes. So it's often recommended just to use an 8 dBi, or to, depending on exactly what your situation was, to kind of confine that in different ways and make a more effective use of what limited range you have for communications. Okay. Down tilt. Either mechanical or electrical. When you down tilt, basically the antenna is electrically a little bit shorter and forces the main lobe of radiation downward. Particularly when you're running, if you're up a 300-foot tower or something. You see this all the time in the cell phone towers. If you ever drive by one, if you can get a good look at them, you'll probably find out the antennas are slightly tilted. The reason for that is because they want to put the signal where it's needed and not point it into another cell where they may be using the channel, or one of their competitors may be using the channel. It benefits everybody just to do it right the first time. Yeah. Okay. The other thing is there is up tilt, which is very, very seldom used. But if you were shooting from, say, a valley up a mountain slope, you might use up tilt. But there's other considerations. If you did something like that, knife edge diffraction could affect the signal and cause it to go over the other side of the mountain. It would not be very reliable on the other side, but it could be possible to pick it up from time to time. This is an example of mechanical down tilt. You can't see the bottom half of this, but there's not really much to see but what you see there, which is, this is actually a border blaster. It's a radio station in San Diego, or not in San Diego, it's actually over the border in Mexico. And what they've done is that they're transmitting power right on the border and pointing it towards San Diego and making advertising money off of it. Since it's Mexican, they don't have to meet as many rules as we do. Like I said, this is actually a treaty violation. They've sent paperwork back and forth between the states to try and figure it out, and so far nobody's found a good solution. They've got about a 60 kilowatt transmitter feeding this thing, which is pretty typical for FM. But what you can't see here is these nice little lines along the back, which are probably imperceivable to you, are actually called parasitic reflectors. They're basically bouncing the entire signal north. And as a matter of fact, if they did not tilt this antenna, you could hear it in Los Angeles. Okay, that's useful. This is with known down tilt. You wind up with the other half pretty much looks identical. It's just flat, it's confined. It goes in one direction. When you throw down tilt on it, you push the signal down, like I said, if you're doing coverage into valleys, things like that. This is not really useful either, exactly. But you can see here with this is an antenna plot. And with 10 degrees of down tilt, you have zero here in the middle. And you can see that the main lobe of radiation is significantly lower, whereas without down tilt, it just extends out. What's interesting to note here is that this is, I think, a 10 dBi or an 8 dBi antenna, and there is some radiation down here at the bottom. It's also possible when using these antennas to create a cone of silence directly below the antenna because of the field that it can operate in. If it has no radiation, pattern directly below it, then you won't hear anything. In fact, with this antenna, you're liable to pick something up, and then at some point you'll fall into this null here, which is area of no signal, and you'll fall out, and then you start picking it up as you get further away again. Loss and attenuation, very important stuff. This is actually one of the really big rules as to why things are the way they are. You've got loss in virtually every device, including amplifiers. Most of what you're concerned about is insertion loss. Any device you insert in the RF path causes loss. Again, most of what we're concerned with is path loss, which is how we get from point A to point B through the air. They have some really nice software to figure this out called path loss, and I don't remember what we paid for it years ago, but I think it was like somewhere between $500 and $2,000. So it's really nice. Figures most of this stuff out for you, but it's always nice to have the grounding here to work from. Yeah, but hey, why pay for software? You can do most of the legwork yourself. Magic numbers here. Of course, this is kind of cut off. Loss in decibels, 96.6 plus 20 log frequency in gigahertz and 20 log distance in miles. Okay, we have, let's say, 2483 megahertz, 3.483 gigahertz. The reason why you figure your loss is that the higher the frequency you operate at, the highest one's going to experience the most loss. You engineer the link for that, and your lower frequency should be fine. So, of course, it's missing the bottom half, which I'm really getting to enjoy, but that's where all the numbers are. And you wind up with 96.6 plus 78995 plus 2602 for 130.5 dB loss for 20 miles. dB is logarithmic measure, so the further you go, things don't necessarily get so bad. You know, going a few more miles may wind up just being 3 dB or so. Okay, total margin. The total margin you've got to work with here is your transmit power minus your coax losses plus the antenna gain minus the path loss plus the antenna gain on the other side minus your coax loss. So when you're running an amplifier, when you're running a half-watt amplifier, transmit power is usually going to be plus 36, so half a watt, plus 36 dBm. You throw in about a dB or so worth of loss. The actual figures may be lower, but usually 1 is a good number to start with. And then plus 23, which is one of the most common Wi-Fi antennas out there that I'm aware of, very popular, is the 23 dBi conifer, which was actually bought by Andrew, which is a 2-foot by 3-foot parabolic dish. Okay, minus the path loss, plus another conifer on the other side, some miscellaneous loss. Most of your amplifiers actually have preamplifiers in them, which is very useful. Like I said, you can get away with running a cheap piece of coax. Well, it's still it's good stuff, but it's cheap compared to his hardline. And you can throw that RX preamplifier into it, which basically can get you over the loss that you'd see in the cable, and then some coax loss there, and your receive sensitivity. Receive sensitivity is a big part of this too. You can't receive a signal below your sensitivity. So if your figure comes, if you're set for -87 here, that's what the the Orinoco spec says, that you can't receive like 11 megahertz or 11 megabits below 87 or so, and you wind up working a path loss, and it shows you your signal being about like 114 dB. You're not going to pick it up. Okay, all these funny numbers add up together to a margin of 47 dB. 5.9's reliability, 99.999% is 30 dB fade margin, roughly. This particular link is 17 dB above that, so it's a pretty reliable link, assuming you don't have FAA radar and other issues that could affect it. You always do have outside influences when doing this stuff. There's little that can be done to control that exactly, but assuming everything else, assuming you don't have any outside sources of interference, this link will be reliable. Passive repeaters. This is a sore point for me because I hear about it so much. I've worked numbers on this before and discovered it's a really great way just to waste money. Passive repeaters are seldom used because they experience twice the path loss. You have the path between antenna A and antenna B, and then the path between antenna C and antenna D. And because you're working with such limited capture area, it's not able to recover enough power to always overcome the loss at the other end. As you can see here, 36 dBm plus a 23 dBi dish minus 130 dB with the path loss. Another antenna, another loss, another antenna, another 20-mile link, another 23 dBi dish, 14 dBi or 14 dB worth of preamp gain, a couple of dB worth of coax loss, 150 dBm. So really the only time that you can use a passive repeater is if you happen to have one end extremely close and you can stay in the near field effects. And like I say, you're talking about perhaps from the ground floor here, maybe the top of the building would be about the only distance you could reliably use it for, and even then it could significantly impact your communications. The comment here from this gentleman is that he's heard of passive repeaters being used to get around mountains. It was actually a very common trick a couple of years ago for some cable systems, but it's dangerous at best. It can work, it can be reliable, but I wouldn't base a business on it. I've heard of years in the past. Somebody wants to get a TV station. They live right below a mountain. They got a buddy who lives on the hill. They convince him to put up a little pole with an antenna pointed at the TV station and then one pointed down the hill, and now he can pick it up. That's one of the funny things, that sometimes it works, sometimes it doesn't. But for the most part, in this stuff, we usually don't worry about it. Of course, more points here. What we got down here is that most cards don't work below -93 dBm max, and that's cutting them all the way back to half megabit if any of them still support that stuff. And like I said, not really work unless one of the links are really short, and it's not really kosher for this kind of stuff. It's just something you want to stay away from. Useless information. Don't turn your access points up unless you know what you're doing. Otherwise, you will crap all over the band and into other groups' segments of the band, which could expose you to FCC liability. And this, they're liable to take a lot more seriously than some of the other issues. This is a spectral plot of a clean WAP, which you kind of miss the bottom part here, but you get the same basic idea. You've got this nice confined signal. That's 22 megahertz wide. So it's still quite a signal there. The dirty WAP pretty well extends exactly in this triangle. And the problem is on this side of the band, you've got MMDS, which is, they've got a lot of different things they can do. Some educational institutions are using that to deliver TV, but down at this end, you've got some ham radio band, but microwave radio, it's not used all that frequently, but if you wind up living near somebody who decides they want to use it, they can really make your life a living hell for it. But again, up in MMDS is where they're more liable to, if they see it, they're more liable to make a suggestion about it. Why to keep it clean? Good, polite engineering practice. Do it right the first time. Also has the benefit of keeping the FCC off your tail in case of a problem. Really not a good idea to mess with hams. They can transmit 100 watts with unlimited antenna gain, and you can't. MMDS will just have the FCC sicked on you. What's really interesting about this is that ham radio does have the spread spectrum limit at 2.4 gigahertz of 100 watts, but they have to use automatic power control. However, most microwave ovens actually have a magnetron in them that generates anywhere from 500 to 800 watts, about 10 megahertz wide. And the FCC does allow hams to use Morse code, CW, continuous wave, and it just so happens the output of a microwave oven is generally regarded as a continuous wave. Now, the hams also have this interesting limit that they can only transmit 1.5 kilowatts at the antenna. So if they happen to be feeding a reasonably large dish, your Wi-Fi card may no longer exist. But if it's up a tower, that's okay. If it's pointed at you, you will feel the pain. Incidentally, they'll also be liable for that too, because you can't do that to people. If you can turn the yeah, right. If you must turn the power up, turn it up by no more than 100%. 21 milliwatts to 50 milliwatts, it should be reasonably okay. 100 milliwatts will be stretching it. The problem is that the amplifier loses its linearity when it goes up in power. This is the same problem with CB radios. You start turning the power up, and the reason why the power goes up is because all this other energy in signals other than the intended signal go up, and it's all added up together in that meter. So you wind up just creating more interference. I suppose that's good if you want to keep the competition away, but it's best for everybody just to do it right the first time. 100 milliwatts, like I said, probably stretching it. OFDM, which is 802.11g, you won't be able to amp it as well as CCK, which is 802.11b. Here's a nice spectral plot of 802.11g. This took a while to capture, mostly because I had to learn how to use the spectrum analyzer. This is 802.11b. You notice that they look an awful lot like each other. Now this garbage down here is actually when the card was scanning, which they have a tendency to do in between packets. So you can see here you've got this really nice round uniform shape. Most of the energy off these ends just don't count. This is the 5 megahertz of division plot, which looks a lot better on my laptop screen than it does up here. But you can see the same basic thing. You've got it kind of round tops there. This is rather difficult to capture, mostly because you're talking about a signal that's there and it's gone very quickly. I think that may actually be in another talk. Spread spectrum was originally known as low probability of intercept. With Wi-Fi, that's not exactly the case. Okay, Fresnel zones. Fresnel zones are a really big important thing. That's the zone where the signal resides between the two endpoints. First Fresnel zone, .6F1, is where 60% of the signal is. For reliable links, no intrusions may be tolerated in the first Fresnel zone. Trees, rocks, houses, etc. You want to make sure whatever it is, you're clear it for that Fresnel zone. And ideally the second and third. Normally you only really start worrying about the second and third when you're shooting over water, because they have odd ways of reflecting up and canceling out the signal that you're sending. Mounting height. Why is this important? For the same reason, to keep the Fresnel zone clear. Multipath is also possible. You have to kind of gauge that one carefully as to exactly how to eliminate it. That's really kind of advanced stuff. Down tilt, of course, Fresnel zone location. Economics. A 6-foot dish at 350 feet on a tower is a big tower, and it's also very expensive. But a 6-foot dish at 50 feet is not going to be nearly as expensive. Realistically, anything beyond 3 feet, and you're probably dealing with a lot more money. Okay. The other part for no zone clearance is to maintain minimum height above the ground in accordance with the bulge created by the curvature of the earth. The Wi-Fi shootout, they kind of had a little problem. 125 miles. You say, wow, that's great, that's wonderful. Curvature of the earth thrown in there, you wind up requiring 2 mountains that are 6,000 feet tall, assuming over flat land. So if there were a mountain in the middle, that link probably wouldn't happen. But if you just wanted to completely base everything flat and say, you know, like Kansas, and completely disregard curvature of the earth, you'd need a 6,000 foot tower on each side. So it's really crazy stuff. More math. They've got this wonderful figure. This is actually from one of Cisco's papers. Most of everything that's in this presentation you can pull off of the web. I've kind of done you all a favor and collated most of it. You can get like 99% of the figures that you need to figure all this stuff out. Frequencies, everything here is specified in mostly in gigahertz, megahertz. This is actually useful down to VHF, so if you want to plot a link, you know, at 150 megahertz between, you know, here and wherever, it should all translate exactly. Fresnel zone clearance. Figure comes out at 61 feet, but this is just the Fresnel zone, and there's more math. This is the earth bulge figure, which is distance between the antennas squared divided by 8, which winds up being 112 feet at 30 miles. Throw it all together, and you wind up with 188 feet, which is the minimum mounting height for your antenna for this 30-mile link. When you hit 200 feet, well, first of all, when you hit anything above 30 feet, you pretty well need a tower. Microwave doesn't lend itself, or microwave radio, because the antenna gain, they don't really like antennas moving all that much. And when you start dealing with anything above 32 feet, you've got fall hazards. Plus, at 200 feet, you have to lamp and light a tower. And register it with the FCC and the FAA. So 198 feet or so is probably the highest you'd want to have anything mounted. And I have a friend of mine who owns a 180-foot tower and only has a 10-foot pole on top of it just to stay under. Okay. Tower trivia. 200 feet and up, got to register and light or paint your tower. If you use strobes, you don't have to paint your tower, but they run 24/7. If you use red lights, you do have to paint. And of course, you still have to worry about people complaining about these birds that flew around your tower and wound up killing themselves somehow. Towers are extremely expensive too. Very expensive. Golden standard when I got into this stuff was a half-watt amp plus an 8 dBi omnivertical. This assumes 1 dB of loss in the coax and connectors and all the rest of that wonderful fun stuff. In reality, the figure may be lower, it may be a little higher. It's just kind of assumed, and you just hope an FCC agent doesn't show up and want to find out for sure. Okay. The FCC maximum effective radiated power is 36 dBm for point-to-multipoint transmitter, and when using point-to-point, the maximum is 44 dBm EIRP, which I believe is somewhere around 50 watts or so, maybe actually higher than that. But the transmitter power must be lower by 1 dB per 3 dB gain over 6 dBi, which realistically speaking isn't a problem until you start dealing with dishes about 6 feet or bigger. Then you start having to cut figures out. The dishes they used at the Wi-Fi shootout at 125 miles, they were not derating for power. I think I remember doing the math once, and this works out to something along the lines of if you're using a 32 milliwatt Orinoco card, you actually have to put attenuation between it and the antenna in order to maintain compliance when using a 12-foot dish. Why so complicated? Well, because it's an unlicensed band. The FCC has their own rules, and they only want you to, pass go on the second Thursday of every month. There's also satellites up at 2.4 gigahertz. Years ago, it was found out that some pretty nifty, innovative ideas they were using. You put the dish at the bottom of the tower. You put a plane reflector up top. it works really well. You have this simple object up top that usually doesn't care about what it's doing, and if you need to fix anything, it's all right there on the ground level. Until they found out that they were getting TV and communications satellites and said, we'll have to change that. Most of the satellites at 2.4 gigahertz that I'm aware of are ham satellites, so usually you don't have to worry too much about that. How much gain does that dish have? Suppose that you just were driving down the road and saw a dish and you said, that'd be neat, maybe I want to take it home with me. You can actually use these figures to figure out more or less if the illumination is perfect, or not perfect, but reasonable, how much gain it would have. Let's see, what did I use here? 4-foot dish winds up working out to 27 dBi, which isn't too bad. It's only about, 4 dBi, 4.4 or so higher than the conifer, but the conifer is it's parabolic. It's not perfectly circular. So you can see where there's gains here, but generally speaking, circular dishes are very easy to find because most of the land-based microwave stuff use it already. The higher the frequency, the better condition the dish has to be in, more perfectly round it has to be. Most of the ones that were used for terrestrial microwave links operate such high frequencies at 2.4 gigahertz. They're great. But there's something else I was going to say, but I forgot what it was. Okay, beam width. Antenna beam width is always expressed in 3 dB points, which is basically the point where the power measures about half of what you're actually trying to send out the middle. 99.9% of all antennas are calculated this way. In this particular instance, of course, it chopped off the figure, which is 62,580 divided by the diameter in feet times the frequency in megahertz, which of course is in the parenthesis, is your bandwidth. So 4 feet, 2483 megahertz, is about 6.3 degrees. So you know that in order to maintain at least half signal strength, you have to be within that 6 degree window. But, you know, it's much more fun just to throw weird numbers in and see exactly what your numbers come out with. So I said, let's figure out what this would be for a 24-foot dish. And at 2.4 gigahertz, it's 1 degree. You know, 1 degree, of course, is a 360th of a full circle. So you can pretty well imagine what it's going to take to keep an antenna that has 1 degree worth of total, you know, signal area effective in that spot, knowing that you have to actually keep it better than 1 degree. We've got another point here, which is the 24-foot dish is also going to have a huge wind load, and it has to be kept in place. The military and other organizations like to use really fancy, expensive antenna positioning equipment that works extremely well, but it costs a boatload of money, but it does the job. AT&T went the cheaper way out, and they just said, we're going to build a really big, strong, sturdy structure and hope for the best. Of course, being an infrastructure geek, found out some of the information about the AT&T microwave stuff was online, pulled off lots of interesting facts. The AT&T microwave dishes, the original cornucopias, which that tower out there does not have on it, exhibit 39.6 dB of gain at 4 gigahertz, 43.2 at 6, and 48 dB at 11 gigahertz. Now, 23 dBi dish is usually about the most I think anybody in this kind of arena is working with, but this gives you an idea of exactly how much antenna gain they're working with. That's absolutely a phenomenal amount of gain, but it's also a very big antenna. You know, I wish that there were other bands that you could get this kind of directivity, but really it's unnecessary unless you really want to, you know, clock people or something. You do using radar at 200 miles. I don't know. But the beam width winds up getting significantly smaller, 2 degrees and then 1 degree, and then finally 0.8 degrees at 11 gigahertz. The higher the frequency, more gain, the same antenna space, but things get a lot more directional. At less than a degree, that really has to be kept in place extremely well, because anything, an earthquake, could potentially knock the link out. Another fact I threw on here is that I found out the AT&T cornucopia antenna has a wind profile of 67 square feet, which is extremely large. Most of the small antennas, 23 dB on a dish or so, you're going to be winding up with 2.3 or so square feet, maybe less. So you can see why they had to have such big towers. Pretty picture of what I'm talking about. Mounted, nice big antenna. It doesn't really show the scale. Another lesson learned with AT&T was channel reuse strategy, which is very important anytime you're doing wireless ISP. You have to engineer the system so that you can reuse as much spectrum as possible without winding up interfering with another node or cell and effectively knocking your bandwidth down because of interference. So what AT&T did here, since all their shots are point to point, is that no path shoots into another path, because all the towers are misaligned with each other, so that it's not possible to shoot into another tower, period. They intentionally offset everything for this reason. Of course, they also used clear Fresnel zones, highly directional antennas, securely mounted, and the original AT&T microwave stuff, they were transmitting less than 5 watts, but they also had a lot of antenna gain behind it. This is another pretty picture I pulled, which looks even worse. But you can see here we've got one tower here, another tower here, and they just basically did this. They would zigzag the entire path if they needed to in order to be able to reuse their channels. And the same lesson applies. You only really have 3 non-overlapping channels at 802.11b, and if you're trying to get from here to Knoxville or here to Huntsville or something like that, you have to have a strategy for being able to make things work. Distance, realistic limits, distance really is your largest limiting factor. Well, not exactly. In 802.11b and G, it's actually the protocol itself. The assumption is who the heck is going to use this stuff to talk more than 20 miles? So they have some timing variables in there, which are, of course, wired into the protocol itself. You cannot adjust them. So the best you can hope for is to actually slip out of this time window and fall into the one behind it. Because of this, most links over 40 miles or so exhibit significant packet loss. If not packet loss, then definitely throughput. This is okay, it got chopped off. Even the Wi-Fi shootout at 55.1 miles and 32 milliwatts is only able to sustain a little less than 150 kilobits per second due to time errors. At that particular time they did it, the link speed was set to 1 megabit per second, not 11. The last link they did set the link speed at 11 megabits, and they were able to pass traffic, but I don't remember the exact figures they used, but it was somewhere around the same ballpark. They wound up slipping out of the second time window into, I think, the third or fourth, and they were taking a significant hit in terms of bandwidth, but let's be honest, 125 miles, who cares about the bandwidth? It's just that you said you did it. Radio bandwidth is half duplex. This has been a hard figure for a long time. They originally saw it in packet radio. 11 megabits is great, it's wonderful, but it's like being on a hub. Effectively, you can only hope for half that at best. And of course, they decide to advertise the things at their signaling rate, not the actual payload rate, which may be less. In practice, 4.5 to 5.5 megabits is really great. Another problem I've become aware of is that a lot of smaller implementations just using commodity hardware. The commodity hardware, particularly regular access points, do not have any form of specialization like some of the alternative methods that have been put out there, like CarlNet. What CarlNet does is they block it and they only move big frames. If you've got a lot of DNS queries or whatever, it'll hold things for a bit and then it'll push them out. With standard 802.11b, you wind up with that stuff immediately getting out over the air. It's not very efficient use of your air bandwidth, and you wind up with there's a significant delay between transmit and receive, and you wind up with so much delay built in between all the packets that your bandwidth just disappears. So, weird stuff. I kind of ran out of stuff at this point because it's like, how many neat and interesting things can you come up with? And apparently I'm not all that inventive. The typical passive detection range is about 3 times that needed to pass information bidirectionally. So if you've got a link that's working reliably at a mile, it may be possible to actually pick that thing up at 3 miles out, assuming all you want to do is listen. Of course, the federales use this sort of technology, CIA, NSA, all the rest of that stuff. There's monitoring posts all over the country, you know, black helicopters, etc. But it's an important thing to keep in mind. You can use a reasonably high gain dish and confine your signal reception area to an extremely small area, say the access point located at the local police department. Kismet, of course, doesn't transmit any packets. And you can also use some of the other tools. I forget the exact names that you can find vendors out there who will sell you basically a Windows version of Kismet. And you know, the downside to this is that a high gain dish. First of all, who's going to notice a misaimed satellite dish? Not too many folks. If you're astute to radio and you happen to see this thing over here, you might think about it. But the big problem is that the higher gain antenna you have, the more noticeable it becomes. And obviously, if you have a satellite dish that's painted camo colors, somebody might kind of wonder. Often the simplest way to cover this up would simply just be to be out there. I would not recommend attempting to break into any police department's wireless access, wireless network, period. I have not done any of this passive reception stuff, so don't ask me any questions. I'm serious, actually. I really don't like getting in trouble with the government. Well, okay. Another interesting point about this, which of course got cut off, is that suppose we inject a couple of dissociation frames. You know, there are DOS attacks that use this method. They go throw packets in the mix, particularly if you're trying to crack web. And when somebody dissociates, the first thing they're going to do is try and reassociate. And darn it, those IP fields are so predictable. They're always there. They're in a known pattern. You build a list of ciphertext, and then you do your processing, and the next thing you know, you've got your web key. So this can be really useful if you just wanted to, throw packets out there, cause their users get kicked off, whatever. You could possibly pick up quite a bit of information. Yeah, that's pretty well close to most of it. I've got some other slides up here that are just kind of goofy stuff. But, of course, the decibels. Decibels is a really funny way of expressing all this stuff, power, relationships, and whatnot. Mostly when you're talking about this stuff, it's decibels relative to a standard. dBm is decibels relative to 1 milliwatt. 3 dB would be 2 milliwatts, but the catch is 3 dB is double your power, but 6 dB is times 5. So realistically, the only things I keep in my head are 3, 6, and 10, since if you know that it's really close to one of those, you can work it out mathematically very simply without having to have a calculator. Of course, 10 dB is 10 times, and 20 dB, for every 10 dB, it winds up being an order of magnitude. Yeah. Yeah, the question here is whether or not the atmospheric effects, 2.4 gigahertz is also known as the water line, which is where water absorbs radiation, and whether or not water absorption can affect RF. That is a factor. Usually, if you're working with a 30 dB fade margin, there's enough built into that margin that unless you happen to live in the Pacific Northwest or something where your humidity is rain, then you're probably not going to have to worry about it too much. Does that pretty well answer the question? Decode. Yeah. Decode makes a valid point here, which is that the other thing to remember is that anything that affects your signal will also affect the noise. If at the water lines, because you have water absorbing RF, it's going to take your noise sources out too, which, for his example, is that he's able to pick up more in the rain when he's out war driving. Of course, I don't do anything in the rain while I'm driving, so. Right. The assumption is more noise from a distance, as the gentleman pointed out. There's lots of noise sources at 2.4 gigahertz and virtually anything. If you try to use your Wi-Fi card close enough to the microwave, it's possible that you could actually fall off the AP. Of course, I went out and found some pictures of the cornucopia horns because I really dig this stuff. It's it's a huge piece of structural steel and lattice and all the rest of that stuff. And what you can't really see too well is this guy who's only about half as tall as the antenna. So here's another shot. We got a guy right down here. The antenna stops right about here, so you can see it's almost 3 times as tall as this guy. And the other one here I've got is that this is actually doesn't show up very well. This is actually AT&T's portable rig they use for setting up the stuff. They threw a 300-foot tower that was sectionalized every 2 or 4 feet into a trailer, drove around, said, hey, can we set up here and test this stuff out? The dishes they actually used were mounted on rollers. They could roll them all the way up to 300 feet if need be. Extremely expensive to put together, build, tear down, but they didn't have all this math figured out. They were kind of armchairing it. These are the standard figures for availability. Can be used for the links, which is 99.999 is 5 minutes worth of yearly downtime. That's not a whole lot, assuming you don't wind up with planes flying over. You do want to make sure that you don't have your fade margins too good, because a figure that I got a couple years ago is that the no damage threshold on an Orinoco is negative 50 dBm. So you can very easily see that if you exceed that, it's possible that your radio card will become deaf. And when it becomes deaf, it's just as bad as throwing more attenuation in there. You may as well just pull the card out and throw it in the trash, or hand it to somebody who's interested in Wi-Fi, but you really don't want causing too much of a problem. And of course you can, here's the only 2 figures. The next one down to the 3 nines, which is 5 minutes, and the next 9 at 6 nines, I think is what it is 30 seconds. Can you manage 30 seconds worth of downtime a year? The AT&T or the Lucent 5ESS in the field achieved 6 nines. In the lab, they only rated it for 5. And that's the rest of the stuff. Any questions? Please. He was wanting to know the infrastructure details and how the stuff was set up. The city that I did the stuff in was Huntsville, Alabama, and we had an existing competitor in the market and really weren't exactly aware of it. And somehow, quite by chance, we ended up using the exact same radios, the hardware that they were using, which use 802.11b cards stuck into a very small PC running a lot of assembly. And somehow we wound up on top of a tall building like this one and actually went microcellular in the business district. Because we were closer, we were able to actually get better coverage than the other fellows who were located up on a TV tower up the hill. So it was a fairly small network. Like I said, we had at least one node there in town, and we had our backhaul, which was always reliable. We had 2 23 dBi dishes, and I think what was it, about a 2-mile shot or something. Torrential rains, and it was doing fine. So we did run into a few issues out in the field, which was if you have a height adjustment, you really need to judge and find out exactly what sort of tilt is going to be required of your antennas, because if you're stuck in steps where you're 0 and then 15 and so on, and the antenna has less vertical beam width than that, particularly if you're, not necessarily vertical beam width, but beam width in the direction that you're interested in, you want to make sure that you don't wind up shooting into the building instead of up on the building where the antenna's at. Otherwise the link can fall down and won't be nearly as reliable. And your customer will be on the phone saying, hey, our network just isn't quite working out here. But, yeah, I think that's most of that. So, any other questions? Oh, look. I actually made it for, I guess, about an hour here, so only about 5 minutes late. But it's not my fault, I swear. Any questions about anything to do with radio, microwave, anything like that? All right, cool beans. Thanks for having me.